Okay, let's get started. So, of course, your exam is tonight. We've been talking a lot about this, and you've been studying a lot, I trust. You're going to PSA 21 sometime after 6:15. I would make sure you have at least an hour, hour and a half. So don't come too late, but you can come after 6:15, okay? And then you can work as long as you want until 9 p.m., okay? Any questions about the exam? 21. Lucky 21. Bring a calculator. There may be a few questions you might need a calculator. But you don't bring your laptop with graphing calculator. So there are questions that refer to graphing calculator. You need to know some of the basics and the mathematics involved in producing a graphing calculator, the things we have done, okay? So graphing calculator is an element of the exam. Yes, it is. Don't get excited. I'm really good at writing multiple choice items. What's that? No, I will have Scantron sheets for you. You don't need to bring a scan sheet. I will have Scantron sheets for you. No, seriously. Don't prepare any differently. Don't prepare any differently. It will test your understanding of what's going on. It's not questions with 5 numbers as the possible answer choices. You're not just computing something and finding the right number answer. Not like that. Okay. So don't let that affect the way you study. Study for whatever format you would study the hardest. Okay. No. Same thing. And then there's still a handful of you. You've made other arrangements. So you are not coming tonight. But if I have not heard from you, you're going to be there tonight. Okay, other questions? We will have homework due Friday. It'll be maybe a half assignment. But we do have class, so homework will be due. Okay? And I have office hours today to help you. Last chance to study, 2:45 to 4:15. Anybody else have office hours this afternoon? And then, but I think, let's see, is it Wednesday? Does she have office hours right after class on Wednesday? No? Monday and Friday? Okay. Well, come find me. So I'm here, ready to help you, 2:45 to 4:15. Later in class. Not that later in class. Other questions? Okay, let's get started. So you read about constant rate of change, and we introduced it on Monday. So hopefully what you read and what you thought about in those reflection questions was helping you further along to understand this principle of constant rate of change. So let's review what we did last time. First we asked, is the size of y relative to x maintained? Meaning, does it stay constant, that relative size? No, clearly, x starts out less than y, and then it ends up being greater than y. There's no way that relative size could stay the same. Then I showed you a different view of this same thing where I focused your attention on just the change in x and the change in y, but the relationship of x and y is exactly the same. So the way those bars are changing together is exactly the same as in the first picture. So now I'm shifting your focus onto the change in x and change in y. What about now? Is the size of the change in y relative to the change in x maintained? Yes. We said yes. And we said, what was that relative size? Can you see that delta y is always 1/2 of delta x? Okay, so that relative size is maintained. So then we said, okay, so if delta y or delta x, the size of the change in y relative to delta x is always 0.5, then we said, wouldn't it be true to say that delta y is increasing half as fast as delta x is increasing? Is that fair? Okay, so this right here, the fact that the relative size of the change of y to the change in x is holding steady, this is this is what constant rate of change is. Okay? So y is changing at a constant rate with respect to x. Okay? So when we talk about constant rate of change, we're focusing on the changes, but we're talking about the quantities x and y. Okay? So y is changing at a constant rate with respect to x. Okay? And the way we know that is by looking at the relative size of the change in y to the change in x. So from your reading, so let's let A, just like before, let quantities A and B represented by variables x and y, okay? So from your reading, B varies with a constant rate of change with respect to A is equivalent to saying what? So if you remember from your reading, B varies with a constant rate of change with respect to A. What's an equivalent statement to that? Yep. Yep, that's true.
The change in B is proportional to the change in A.
Right, exactly. Changes in B are proportional to changes in A. So those are equivalent statements. This is what it means to have constant rate of change. The change in one quantity is proportional to the change in the other. And then we saw these mathematical results of that. So mathematically, what does it mean for the change in B to be proportional to the change in A? So that's what some of you were saying. Okay, right? And then what was the other one? Right, so now we're actually talking about values of these quantities B and A, we're using x and y, okay? So the first thing is that the change in y to the change in x is constant, right? It's proportionality, right? Proportionality means you have a constant ratio, okay? And then the other thing is that the change in y is a constant multiple of the change in x. So on the left, we have a quotient. We have a quotient, and we know quotient means relative size. Okay? So the size of delta y relative to delta x is constant. That's what that statement on the left says. And on the right, what's the right about? What principle is the right about that we've talked about? What is it? Constant multiple, right? We have the change in one quantity. We multiply it by a number, we get the change in another quantity. That's the idea of constant multiple. The change in y is a constant multiple of the change in x. Both of these are the mathematical results of saying that changes in B are proportional to changes in A. Let's just say changes in A. Okay. All right, so let's look at this thing again. It's the same thing. Is the size of delta y relative to delta x staying constant? Is the size of delta y relative to delta x staying constant? Yes. What is that constant? 0.5. Is the change in y a constant multiple of the change in x?
Yes.
What is that constant multiple? 0.5, okay? K is 0.5, that's the point. So that relative size, that ratio of delta y to delta x, in this example, is 0.5. It's also, we talked about this Monday, that constant ratio, or that relative size, is the constant multiple. It's the number you would multiply delta x by to get delta y. This should make sense. Okay, so this is the basics here of constant rate of change. So I've got those up there. We're going to look at an example. So we're going to keep this stuff in mind, right? If you've got constant rate of change, these are our two mathematical ideas that we have. So here's an example. You buy a certain trail mix. It costs $2.75 per pound, which means the cost in dollars is always 2.75 times the number of pounds that you buy. Okay, so I'm going to give you a set of variables. I want you to define each one completely and precisely. Okay? So in this situation, what is x? If you're writing out phrases according to this example. X is what? Y is what? Delta X is what? Delta Y is what? K is what? Go. So how would you identify all these variables for this context? Go. Okay, I'm gonna call on some of you today. I don't know your names. I need to get a list of names, so I will get a list of names. So I'm just gonna call you out by what you're wearing. All right. So right here in the tie-dye shirt. What did you say X was? You know what? Not sure. Okay, right. Next door.
I got it.
The number of pounds of trail mix. What do you think? That's it. Number of pounds of mix. Okay, you're on a roll. Keep going. What do you think Y is?
The price of the trail mix.
The cost, right? So the cost of X pounds of trail mix. The cost of X pounds of trail mix. Okay, somebody new. Bullseye here. Delta X, what would that be?
Yeah, I said delta X is the change in cost.
The change in the cost. Agree with that?
Oh, the number of pounds, sorry.
Change in the number of pounds, right? Change in the number of pounds. And delta Y? The change in the cost. Okay, what is K in this situation? Okay, so but what if you were to write something out? What is it? It's the constant rate of change. It's the constant rate of change.
Would you want us to write this constant rate of change or specify it as cost per pound?
It's both, right? So it's both.
This
Yeah. Yeah, there's different ways to say K, yeah.
Would it matter if we switched it up and had X as the cost of pounds in the mix and Y as the number of pounds?
It would be inconsistent then with this above, the way we use Y and X above. Right? So if delta Y is K delta X, and if K is 2.75, then Y has to be the cost and X has to be the number of pounds. Does that make sense? So to be consistent with what we have up there, it matters. But if we didn't have that, then if you wanted, you could switch them. Yeah. Okay, so I want you to write an expression using these variables that would compute the rate of change. So what expression using some or all or a few of these variables would compute the rate of change? What would it be?
Change,
Yeah, go ahead.
change in cost over change in pounds.
Just use the variables. Just use the variables.
Delta Y over delta X.
It's delta Y over delta X, right? That's what we said. The constant rate of change is K. It's delta Y over delta X. Okay? What about an expression that uses these variables to compute the change in cost for a change in the number of pounds? So I want to compute the change in cost given a change in the number of pounds. So what expression would you write with those variables? Delta Y equals K delta X, right? And you could put in 2.75 if you wanted to, right? Delta Y equals 2.75 delta X. Any questions? So this idea, so when you get a real world situation, a context like this is so important to get started. Okay? So this may seem easy because I'm holding your hand and I'm giving you so much structure, but that's something you need to be able to do to get started. Okay? So we'll keep practicing it. All right, so after scooping some mix into your bag, you decide you want to buy more. The additional cost you will pay for 1.5 more pounds of trail mix is 2.75 times $1.5. Okay? In this scenario, what is delta X? What is delta Y? And what is K? Go. Okay, how about green shirt in the back row? How'd you do? What delta x?
1.5.
He wants 1.5 for delta x. What are the units on that? 1.5 pounds. Okay, keep going. What's delta y?
Here we do the product of those 2.75 times 1.
So you're saying it's that expression 2.75 times 1.5. You're saying delta y is 2.75 times 1.5. Agree? And what is k? 2.75. Got it. Anybody have a question? So, again, seems easy, but this is how you make sense of the situation, right? You define variables, and you make sense of the numbers that you're given in terms of the variables you have, and our construct, our mathematics of constant rate of change. Okay, next you remove 0.4 pounds from the bag and return it to the bin. Go. When no one's watching, right?
We're still trying to find the same.
It's the same context.
Right, we're just.
Yeah, you just do three things. What is delta x? What is delta y? What's the okay, how about in the black shirt right here? Did you get it? No? What about that right next to her in the yellow shirt? What's delta x here? He wants negative 0.4. Agree? Negative 0.4. And what is delta y? What's the red shirt? 2.75 times negative 1.4. Or 0. Negative 0.4. Let's write this out. So this one was 0.4 pounds? Just testing you. All right, this one is? And K? Still 2.75. And what are the units on this? Dollars, right? And this was dollars per pound. And so then delta y turns out negative. Does it make sense? What is the meaning of that? You're going to get some negative number of dollars. What's the meaning?
It means that you're not paying for it. You don't have to pay that much. It's subtracted.
Yeah, so your cost is going down, right? Your change in cost is negative. So your cost isn't negative, this is your change in cost. So it goes down, so it's negative. Cool, all right. New scenario. A soldier lowers, let's say lowers, an American flag from the top of the pole at 0.8 meters per second, meaning that in any period of time, the number of meters that the flag descends is 0.8 times the number of seconds in that period of time. Make sense? Okay, so one of the variables is the height of the flag in meters. So in order for us to all be on the same page, there's kind of a couple different ways to do this. So I'm going to tell you that one of those is the height. Now I want you to define all five for this scenario: x, y, delta x, delta y, and k, if one of those is the height of the flag. Go. Think you got it? Let's give it a try. Kyle, you're up. What is x in this situation?
X in this situation is the number of seconds elapsed.
Okay, number of seconds elapsed. So whenever you define a time or a distance quantity, you want to always include the reference point. So number of seconds elapsed
Since the soldier started lowering the flag.
Yeah, since the flag was at the top of the pole, or since the soldier started lowering the flag, something like that. So different ways to say it, but you want to, whenever you define time or distance quantities, always give that starting reference point to be specific. Okay. So number of seconds since the flag left the top. Okay. Why?
Why isn't that?
Go for it.
Oh, why? Okay.
Yeah. Sorry. No, not.
Um,
I do ask why a lot, right?
variable y is the height from the ground in meters.
Okay. So the height of the flag in meters, exactly. Okay, so then what would delta x represent? How about the blue striped shirt back there? Yeah. What would delta x be? Change the number of seconds. So like an interval of time, right? Some interval of time. Change in the number of seconds. Keep going. What's change in y? Change the height in meters. Okay? And what is k in this case? What is it? 0.8 meters per second. Agreed? Okay, so what's happening to the height as x increases? Going down, right? Therefore, constant rate of change is negative 0.8.
If we define our y as the height of meters from the top of the pole, would we keep it as positive 0.8 though?
The distance from the top.
Yeah.
Distance from the top of the pole would be positive 8.8.
But in this case, we're measuring it from the bottom.
I told you one of them had to be defined as height. So that's why. Yeah. But if y was the distance from the top of the pole, then that k would be positive. Yeah. Okay, write an expression using these variables that computes the constant rate of change. The constant rate of change using these variables. And they all said together? Delta y over delta x, and that equals? Negative 0.8. Negative 0.8. Okay, write an expression using these variables that computes the change in height for any change in time. The y equals? Negative 0.8 delta x. So this is, you use the constant multiple. If you knew the change in x, use a constant multiple to find the corresponding change in y. Constant multiple reasoning that we've worked on, okay? How much does the height change from 4 seconds to 7.2 seconds since the flag left the top of the pole? What is delta x? What is delta y? What is k? Go. How much does the height change from 4 seconds to 7.2 seconds since the flag left the top of the pole? Okay, let's see. How about right here in the yellow? Yeah. Yeah. And yeah, 3.2. How'd you get that? change in a quantity is final value of the quantity minus initial. She said 3.2 seconds. Agree? Okay, change in y. Tristan.
For the change in y, I got 3.2 times negative 0.8, which would result in the change in y. On the top of the flag, over the 3.2 seconds.
And what would our units be?
Meters. Are we in meters?
Yeah, meters. Again, we're going to get a negative value for this change in y. Doesn't make sense. Why does it make sense that change in y is negative? As that time goes by, the height decreases. So the change is negative. And k is, again, still negative 0.8. Units are? Okay, how much does the height change from 10 to 13.2 seconds? How much does the height change from 10 seconds to 13.2 seconds? So lots of you are saying it, hopefully you thought it. The same amount, right? The same amount, because it's the same change in time. So if you have the same change in time, you're going to get the same, you're going to get the same change in distance that we got before, the same change in height. Okay, so this is actually a kind of a third way to think about constant rate of change, is that we could, up here we could say equal changes in x what happens? So does it matter where I look? Does it matter which 3.2 second time interval I look at? What will happen to the flag? It's going to go down the same amount. So if you get it, so equal changes in x applied anywhere results in yeah. So yeah, the idea is that the changes in y then will be equal. So just to make sure, we don't want to use the word equal because we don't want to kind of imply that change in y is equal to the change in x. That's not true, right? So it helps, you can say, result in consistent changes in y. And then you know that you don't get confused and maybe think that the change in x equals the change in y. That's not true. So equal changes in x result in consistent changes in y. So this is kind of another kind of result of constant rate of change.
Changes in y.
Oh, thank you. Yeah, I already wrote changes. Not changes in delta y, okay? Anyone thinking this? Getting nervous? So, if you're paying attention, and if you got it, you should be able to, so just stay with me for a second here. Constant rate of change of y with respect to x is, you should be able to finish that statement right now if you followed Monday and homework and today. Okay, so finish that statement in your mind. Maybe take turns saying it to each other. Okay, go. The constant rate of change with y with respect to x is, how would you precisely and meaningfully complete that statement? Go. Okay, let's hear what you thought. Let's see. How about in the pink and future right here? Yep. How did you finish the statement? The constant rate of change of y with respect to x is delta y over delta x. Is that right? Okay, but what's that? Okay, that's K isn't very, that's just a letter.
Relative size
What relative size?
Of y with respect to x.
Almost.
Or the change in y with respect
Yeah.
to change in x.
Just the relative size of the change in y to change in x. So if that's what you wrote and said to your neighbor, good job, A+, okay? Constant rate of change is the relative size of the change in y to the change in x. Well, I've got news for you. Okay? The derivative of y with respect to x is the change in y with relative size. Sorry, it's delta y over delta x, which is the relative size of the change in y to the change in x when delta x is very small. It's the only difference. If you've got very, very small delta x, derivative is the same meaning as constant rate of change. So we've already started doing derivative. You just didn't know it. So hopefully you're less nervous. So it's not about algebra and cranking out formulas. It's about something meaningful. It's about quantities, right? It's about how one quantity is changing relative to another. It's about how one quantity is changing relative to another. And this relative size, this quotient, this relative size, is this number that's just packed with meaning. And so that's the derivative if delta x is very small. Question over there.
Why does the change in x have to be very small?
So we'll get into more details, but if delta x is not very small and you have constant rate of change, but it's not derivative. Because with derivative, you can look at a rate of change that's changing. Okay, so the idea of derivative is we can look at a relationship where the rate of change is changing. If you look at delta x small enough, then you can think of it as constant rate of change in that little tiny delta x. Does that help? Yeah, but we'll talk a lot more about that.
So, like when you say delta x is small, you're saying like at a smaller instant of a changing change, you can look at. I'm not sure.
No, in our examples, we did delta x. Like you did it like what'd you do? Delta x of, you added 1.5 more pounds of trail mix, right? So that's not a small delta x, right? That's not a small value. Or like change in time. So what was the change in time in the light bulb? 3.2 seconds. That's not a small change in time. Okay? A micron of a second, that's a small change in time. Or a millisecond. That's what we're talking about. Okay? Top hat. Let's do top hat.